Alright, let's go. Number 10. The baby universe hypothesis. Lee Smolin was not trying to explain where universes come from. In 1990, working at the Perimeter Institute, he was trying to solve a much smaller problem: why the constants of nature in our universe seem so unusually well-tuned for forming stars and black holes. Standard cosmology treats those constants as fixed accidents, set once at the Big Bang and never touched again. Smolin's calculations suggested something else. He proposed that every black hole singularity does not end in nothing. It bounces, and on the other side, a new universe is born, expanding into dimensions the parent universe cannot access, carrying constants that are slightly mutated from its parents. A universe that forms black holes efficiently produces more offspring. Over long enough timescales, natural selection favors universes like ours. Smolin published the idea as cosmological natural selection, and the disturbing part was not the theory. It was that the theory made a testable prediction. Tweak any fundamental constant and black hole formation should drop, and later analysis found this holds for several constants scientists checked. Critics point out the offspring universes are causally disconnected by definition, meaning the theory can never be confirmed through direct observation, only through indirect statistical checks on our own constants. Other cosmologists have argued the correlation Smolin found is coincidental, a side effect of ordinary selection bias rather than genuine reproduction. Neither objection removes the mechanism from the mathematics. No one has found a clean way to kill the idea. No one has found a way to confirm it either. Every stellar mass black hole in the Milky Way, roughly 100 million of them, may be a birth canal for a universe we will never see, running on physics we did not design and cannot inherit. You are, on this account, standing on the inside of one branch of an unobservable family tree. How many universes down the line are we, and does it change anything if we never find out? Every black hole in that count is calm from the outside. What happens past the horizon is a different argument entirely. Number 9. The negative mass interior. Roy Kerr was not trying to describe anything exotic when he solved Einstein's field equations for a rotating mass in 1963. He was closing a gap. Schwarzschild's solution from 1916 only worked for objects with zero spin, and almost nothing in the universe has zero spin. Standard general relativity says gravity only pulls, in every regime without exception. The Kerr metric held to that rule everywhere except one place. Inside the inner Cauchy horizon of a rotating black hole, the mathematics flips the sign on the gravitational term. An object approaching the ring singularity would feel repulsion instead of attraction. Physicists Brandon Carter and later Kip Thorne worked through the consequences across the 1970s and confirmed the reversal was not an error. It falls directly out of the same equations that correctly predict every gravitational wave LIGO has measured since 2015. The proposed fixes have not resolved it. Some argued quantum effects would destroy the inner horizon before anything reached it, a conjecture tied to the strong cosmic censorship hypothesis, but 2018 work on charged black holes found configurations where the instability was too weak to guarantee this. Others argued it was purely mathematical, with no physical horizon ever actually forming that way in a real astrophysical collapse. A third camp proposed the region simply gets replaced by a more complicated quantum structure before anything reaches it, sidestepping the problem rather than solving it. Neither claim has been settled. Every black hole that formed from a spinning star, which is effectively every black hole that exists, carries a hidden interior region where our most tested description of gravity predicts gravity running backwards. We have zero observational access to it and zero way to rule it out. If gravity reverses in a region we cannot see, what else about that region are we simply assuming? Number 8. The Penrose Process products. Roger Penrose was not trying to build an engine. In 1969, he was working through the theoretical energy budget of rotating black holes, a purely mathematical exercise in general relativity. Standard physics treats a black hole as a one-way trap. Energy falls in, nothing organized comes back out except thermal radiation. Penrose's math said otherwise. Inside the ergosphere of a spinning black hole, spacetime itself is dragged around so violently that a particle can split in two, with one fragment falling and carrying negative energy, and the other escaping with more energy than it started with. Done correctly, the process can extract up to 29% of a rotating black hole's total mass energy. For decades it stayed theoretical, dismissed by many astrophysicists as a mathematical curiosity requiring conditions too delicate to occur in nature. Then in 2021, a team led by Luca Commisso at Columbia University published evidence in Physical Review Letters that magnetic reconnection inside the ergosphere of spinning black holes can accelerate plasma particles into exactly this negative energy configuration, implementing the Penrose process by physical rather than exotic means. The extracted energy does not disperse randomly. It gets funneled into relativistic jets, some stretching millions of light years, the most coherent, organized energy structures known to exist anywhere. Every active galactic nucleus with a spinning black hole may be running this extraction process continuously, right now, converting the geometry of spacetime itself into structured energy that crosses the observable universe. The most efficient machine in the cosmos was never built. It fell out of the math, and then someone found it running. Number 7. The Hawking radiation correlation problem. Stephen Hawking was not trying to threaten quantum mechanics in 1974. He was checking what quantum field theory predicts happens at a black hole's event horizon, expecting a tidy, uneventful null result. Standard quantum mechanics has one unbreakable rule. Information is never destroyed, only scrambled. What Hawking found was that black holes emit thermal radiation, and if that radiation is truly random, all the information about what fell in is erased when the black hole evaporates. That contradiction became known as the black hole information paradox, and it has resisted resolution for 50 years. Earlier proposals had already failed to satisfy the physics community. The idea that information simply leaks out through wormholes to other universes was widely rejected for creating more problems than it solved, and the notion that black holes evaporate completely with information genuinely lost was rejected because it breaks a symmetry quantum mechanics has never been observed violating anywhere else. In 2016, Hawking, Malcolm Perry, and Andrew Strominger proposed instead that black holes retain information as soft hair, zero-energy photons, and gravitons imprinted on the horizon. In 2022, physicist Suvrat Raju at the International Center for Theoretical Sciences published calculations suggesting the radiation is not random at all. Each photon looks thermal individually. But across the full emission history, a pattern of subtle correlations exists between them. No single photon reveals it. The full sequence does. If Raju's picture holds, every black hole in the universe is not simply leaking energy into the void. It is slowly writing an increasingly complex, entangled structure into the radiation field surrounding it, one photon at a time, encoding the complete history of everything that ever crossed its horizon. Somewhere in the radiation leaving every black hole in the sky, your information may already be being written down. Number 6. The Planck star bounce. Carlo Rovelli was not trying to eliminate singularities when he began working on loop quantum gravity decades earlier. He was trying to make gravity and quantum mechanics mathematically compatible at all. Standard general relativity says matter collapsing into a black hole is crushed without limit, all the way down to a point of infinite density. In 2014, Rovelli and Francesca Vidotto at Aix-Marseille University published a paper in Physical Review D arguing that loop quantum gravity forbids this. Collapsing matter compresses only until it reaches Planck density, the maximum density the theory allows, and then it bounces back outward. Here is the pivot. From outside the black hole, that bounce takes billions to trillions of years to complete. From inside, it takes Planck time, 10 to the power of minus 44 seconds. The rebounding matter, a Planck star, sits compressed to the theoretical limit of physics for what looks from the outside like the black hole's entire lifespan. Objections followed quickly. Critics argued the bounce would be gravitationally unstable and disperse before completing, or that Hawking evaporation would finish the black hole off before any bounce could occur at all. A further objection held that the extreme time dilation required is itself unphysical, requiring fine-tuning no known process could produce naturally. None of these objections has been conclusively resolved either way. If Rovelli and Vedato are correct, every black hole in the universe currently contains a star compressed past the edge of anything physics can otherwise describe, mid-bounce. And the oldest ones, formed in the universe's first billion years, may be approaching the point where that bounce becomes visible as a burst of radiation. A star older than most of the galaxy may be finishing something it started 12 billion years ago, and we would only find out when the light arrives. Number 5. The fuzzball conjecture. Samir Mathur was not trying to abolish the singularity when he began working through string theory's description of black hole microstates in the late 1990s at Ohio State University. He was trying to count them, a bookkeeping problem in quantum gravity. Standard general relativity insists every black hole hides a singularity at its center, a point where physics simply stops working and the equations return infinity. Mathur, working with Oleg Lunin, found the string theory calculation refused to produce one. Instead, the mathematics described something else entirely. A black hole as an enormous, horizon-spanning object built from string theory excitations, with no interior, no singularity, and no information paradox. Because information sits encoded on the stringy surface itself, rather than vanishing at a central point. They called it a fuzzball. In 2023, Mathur published updated calculations showing quantum gravity corrections near the horizon become comparable in size to classical gravity itself far earlier in the collapse than anyone had assumed. Meaning the fuzzball structure should dominate almost immediately. Competing camps still favor the classical singularity picture, arguing the fuzzball construction only works cleanly for special highly symmetric black holes rather than the ordinary rotating ones scattered across the galaxy, and no observation has distinguished between the two pictures. If Mathur is right, every black hole in the galaxy is not an empty void wrapped around a mathematical point. It is a seething, string-scale quantum object we have no equations to fully describe, and anything that falls in is not crushed. It is absorbed into something we cannot yet name. Nothing falls into the dark at the center of a black hole, because on this account. There may be no center and no dark to fall into. Every entry so far describes what a black hole might be doing to what falls in. The next 4 describe the argument over whether a black hole can even keep its secrets. Number 4. The firewall paradox. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully were not trying to overturn general relativity in 2012. They were trying to check whether 3 separately reasonable ideas about black holes, that information escapes, that the horizon is an ordinary patch of empty spacetime, and that quantum entanglement cannot be shared 3 ways at once, could all be true simultaneously. Standard physics, built on Einstein's equivalence principle, says an observer falling through a black hole's horizon should feel nothing unusual at the boundary, smooth space all the way through. The team, working through the entanglement bookkeeping required for information to escape via Hawking radiation, found the 3 assumptions could not coexist. Something had to break. Their proposed resolution, published on RXIV and widely debated afterward, was that the horizon is not smooth at all. It is a wall of high-energy quanta, a firewall that would incinerate anything crossing it, directly contradicting a century of general relativity. Proposed fixes multiplied. Complementarity argued that no single observer ever sees the contradiction directly, so it might be harmless. Non-locality proposals allowed information to leak out through subtle correlations without a wall at all. Leonard Susskind and Juan Maldacina's 2013 ER-PR proposal was itself partly a response to this exact crisis. None has achieved consensus among the physicists who first raised the problem. If falling through certain black hole horizons ends not in a gentle transition, but in immediate destruction at the boundary, one of general relativity's oldest and most trusted assumptions is simply wrong for objects of this kind, and no one currently agrees on which one. Physicists cannot agree on what happens the instant you cross the horizon. and the three ideas at the center of the disagreement each seem individually undeniable. Number 3. The ER/EPR conjecture. Juan Maldacena and Leonard Susskind were not trying to unify wormholes with quantum entanglement when they began circling the firewall debate in the early 2010s. They were trying to find any resolution that preserved both smooth horizons and information conservation without contradiction. Standard physics treats general relativity's wormholes, Einstein-Rosen bridges from 1935, and quantum mechanics' entanglement, the Einstein-Podolsky-Rosen paradox from the same year, as entirely unrelated phenomena from different branches of physics that happen to share an author. In 2013, in a paper titled Cool Horizons for Entangled Black Holes, Maldacena and Susskind proposed they are the same thing described two different ways. Two entangled black holes are connected by a wormhole, and any pair of entangled particles anywhere is connected by an infinitesimally thin version of the same bridge. The implication is not confined to black holes. If ER equals EPR, every entangled particle pair in every laboratory on Earth is linked by a microscopic wormhole, too small and too unstable to traverse, but geometrically real by the same logic that makes black hole wormholes real. The conjecture remains unproven, and critics note it has not yet produced an independent testable prediction beyond restating the correlation it was built to explain. If it holds, geometry and entanglement are not just related. They are one phenomenon, and it exists inside your body right now, in every entangled particle any experiment has ever produced and left running. Somewhere in a physics lab, entangled particles may be connected by a bridge too small to ever cross, built from the same geometry as the inside of a black hole. Number 2. The Gravistar alternative. Powell Mazur and Emil Motola were not trying to invent a rival to the black hole in 2001. They were examining a technical instability in the standard collapse calculation, checking whether quantum vacuum effects near the would-be horizon had been properly accounted for. Standard theory says a sufficiently collapsed star crosses an event horizon and continues collapsing to a singularity, with nothing able to stop it. Mazur and Motola's calculation suggested collapsing matter could instead undergo a phase transition just before reaching that point, converting into a thin shell of ultra-dense material surrounding a core of vacuum energy with negative pressure. A gravitational vacuum condensate star, published later in the Proceedings of the National Academy of Sciences in 2004. A gravistar has no horizon and no singularity. It would look nearly identical to a black hole from any external measurement available today, mimicking its mass, its gravitational lensing, even much of its gravitational wave signature. Attempts to distinguish the two have focused on gravitational wave echoes predicted to appear microseconds after a merger signal if a hard surface exists instead of a horizon. LIGO searches through 2020 found no confirmed echoes, but the sensitivity required to rule gravistars out entirely does not yet exist, and several teams have argued the search methods used so far were not sensitive enough to detect a signal even if one were present. Every object we currently call a black hole may or may not have a horizon at all. We have not yet built an instrument capable of telling the difference for certain. The objects we call black holes across every textbook and every telescope may not have an edge of no return at all, and we cannot yet prove otherwise. Number 1. The remnant hypothesis. Yakir Aharonov, Aharon Kasher, and Shmuel Nussanov were not trying to save quantum mechanics from black holes when they began the calculation in 1987. They were tracing what Hawking's evaporation process actually predicts happens in the final moments of a black hole's life, expecting it to simply vanish. Standard semi-classical physics says a black hole radiates away its mass smoothly until nothing is left, information included, which is precisely the version of events that created the information paradox in the first place. Their calculation found the standard picture breaks down before the end. As a black hole shrinks toward the Planck mass, the same scale where quantum gravity effects that Rovelli and Mather invoke elsewhere become unavoidable, the evaporation process should not run to completion. It should freeze, leaving behind a stable Planck scale remnant, roughly 10 to the power of -5 grams. That never finishes evaporating. Every scrap of information ever swallowed by that black hole, an entire dead star's worth in some cases, would remain locked inside an object smaller than a bacterium. Forever, the proposed fixes have their own costs. If remnants exist, quantum field theory calculations suggest they should have been pair-produced constantly, since the early universe in numbers large enough to noticeably affect cosmic expansion, and no such effect has been detected in any cosmological survey conducted so far. Some theorists have tried to rescue the idea by proposing remnants are rarer than the naive calculation suggests, though no one has produced an agreed mechanism for why. If remnants do not exist, we are back to a universe where information is genuinely destroyed, breaking a rule quantum mechanics has never been caught breaking anywhere else. Every black hole that has ever fully evaporated in the history of the universe either violated quantum mechanics on its way out, or left behind something smaller than an atom that is still holding, undisturbed, everything it ever consumed. The universe is not confused about what happens inside a black hole. We are. Every entry on this list sits not at the fringes of physics, but inside its most rigorously tested frameworks: general relativity, quantum field theory, string theory, loop quantum gravity. Each one independently arriving at an interior we cannot observe and cannot rule out. The math keeps working. The disagreement is never about whether the equations are right. It is about what they are quietly describing underneath us, in every black hole in every galaxy, including the supermassive one at the center of our own. If you want to see more videos like this, click the video on screen now.